Oh, I guess I didn't ask you if you can see my screen. Do you see the presentation? I think so. Yes. All right. Good. Great. So we left off at the group membership last time, I think, and yeah, the plan was to continue from there, obviously, and then finish the chapter with consensus variance, and then move on to the last chapter, chapter 4, and do roughly 50% of that chapter, and then we will do the rest on Monday. But I had some messages from students regarding pseudocode, that it was difficult to follow the pseudocode, but yeah, this student didn't tell me which pseudocode yeah, it didn't tell me which pseudocode, so I don't know if it was the Paxos pseudocode or if it was some other pseudocode, but yeah, if you would like me to repeat, for example, the Paxos pseudocode, I can do that, or another algorithm. But yeah, please, if you feel that I need to repeat or yeah, one algorithm or several, then just let me know which one you are referring to, because yeah, I don't know when you just say the pseudocode, because it can be any algorithm. So yeah, just because we have actually time to take a look on Paxos again if you feel there's a need. All right, and also if you have troubles with finishing the labs, either something with your own self or with your group partners or anything else, to try to reach out to me or the TAs as soon as possible, and don't wait till after the deadline before you give us notice of anything, because we want you to all finish the course and also the labs. Yeah. Okay. Anyway, let's get starting on this group membership. Yes. As I mentioned last time, that and also you saw from that tree, that when you implemented the failure detector, at any point in time, they might have different views on which processes are correct and faulty. Just as it's shown here in the sequence flow. Yeah. So the group membership abstraction provides a consistent way or consistent information about which process have crashed and which are correct, and also it has an abstraction for coordinating, joining, and leaving the system for processes. To maybe sometimes in the literature we can find something like a graceful exit or something like that, but yeah. Anyway, it has the membership of a group. It's called the view, and it's a tuple, and I suppose all of you know what's a tuple, which is basically two or more variables clustered together like this. So for each view identifier, there is a unique set of members in that particular view, and all the processes they agree on who is part of the group. Yes, so right here we only consider crash failures, so not Byzantine failures. And the module description, it's seen here. Yeah, one thing maybe I forgot to mention is there is a monotonicity property here, so that the ID of the view is always increasing, so it never goes back. It's kind of similar to like rounds that you had. It was always increasing. Yes. So the four properties here, there is the agreement property or uniform agreement that you will find in consensus algorithms, and the two properties which we are we will look on in the algorithm. It's the completeness property. If a process P crashes, then eventually every correct process installs a view such that P is not part of M. So this captures that when a process crashes, everyone will detect that crash and will exclude that process from the membership. Yes, and accuracy. If some process installs a view with Q not in the membership, then Q has crashed. So it's those two properties that we will see here in the algorithm. As you see here from the usages of this algorithm, it uses the consensus, like here they just call it uniform consensus, and the failure detector. So the group membership is a kind of combination between a consensus and a failure detector. So initially, the group membership starts off with everyone is correct, and it will be the view one, and whenever a crash is detected, it excludes this from the correct set, and yeah, so whenever or before a crash is detected, the algorithm is completely idle, and whenever the crash is detected, it goes to this event here when whenever the correct is subset and not or the let's say the subset and not equal of M. So there is less processes that are correct that is in M, and this waiting flag is false. Then it increases the round, sets this waiting flag. So this waiting flag is just to ensure that it doesn't try to install a new view before it has reached a consensus on a previous one, and then it proposes this view with those processes for the rest of this system. And yeah, if they reach consensus on that, so really the consensus part, it's captured in the underlying layer. And remember that it's important that things arrive in the same order. Yeah, when there is a decision made by the consensus layer, it sets the waiting flag to false again and installs this new. So this last line, it's the actual installation of the view, and this is triggered up to the application layer. So the sequence flow looks like this, and did you have a question or something? Maybe you just forgot to mute. Yes, so if we go back to this sequence flow here, it's kind of showing the same thing as we saw here, that whenever there's a crash, eventually these two will detect the same thing and have the same view. But here it's even more fine-grained that we can see we have 4 processes, and in initial view, view ID 0, all of them are in the membership, all of them are correct. And then 2 of them crashes, and you see that the failure detector of R detects that Q crashes, but the failure detector of S detects that P crashes. And this is the value that they use to propose in the consensus instance. And what is that you have to keep in mind here is that actually in the view 1, they reach consensus of Q, R, and S are correct. And you can see that the process R, it actually goes along to have this as the view, even though it already knows that Q is crashed. So and this is because that it was process S that proposed the value before R. So after this, then R proposes a new values for and tries to install a new view. And yeah, they reach consensus on this. The process also detected that Q crashed, and yeah, it installs a new view. So yeah, and then they have added that the process R detects that P crashed after it was already in view 2, but you can see that process R was able or removed process P from the view, even though it didn't detect it from its payload detector. It was only detected through the consensus instance. So these two crash events here, they are not necessary for the view to be consistent. So that's group membership. Is it okay? Maybe. The next thing, that's what they call asynchronous communication. And yes, I wrote this here. It's kind of an abstraction that's a combination of reliable broadcast and group membership. And yes, group membership was already a combination of consensus and failure detector. But the idea here is to try to capture this particular problem, that the process B can deliver the message M broadcasted by a process Q that fails and then installs a new view. Another process may deliver M after installing the view. So the problem is depicted here, that one process delivers the message and afterwards installs the view, whilst the process 3, it first installs the view and then delivers the message. So that's that.